The standard model of particle physics is the most precisely tested theory in the history of science. Not approximately, not in some narrow domain. Across 50 years, every particle accelerator ever built, thousands of independent experiments, the standard model has not produced a single confirmed contradiction with measurement. That is what greatest achievement means, measured honestly. Now let me tell you what it doesn't include. Gravity, dark matter, dark energy. The reason there's more matter than antimatter in the universe. The values of its own 19 fundamental parameters. The standard model describes roughly 5% of the universe's total energy content, with extraordinary precision, and has nothing to say about the other 95%. Both of those things are true simultaneously, and if you can hold both without resolving the tension, you're ready to understand what the standard model actually is. Most people, when they think about the standard model, picture a table. Quarks, leptons, bosons, a periodic table of particles, a zoo. You learn the names and you know the theory. That picture is wrong, not as a summary, as a description of what the theory is. The standard model is a quantum field theory built on a specific mathematical symmetry. The symmetry group is written SU of 3 times SU of 2 times U of 1. That's 3 symmetry groups multiplied together. This symmetry is the theory's spine, its deepest structural feature. Everything else, every particle type, every force, every allowed interaction, follows from the requirement that the theory remain invariant under this symmetry. The particles are not inputs to the theory, they are outputs. They are what you get when you ask, what quantum field theory is consistent with SU3 times SU2 times U1 symmetry, with special relativity, and with the mathematical requirement that it produce finite predictions? The answer is essentially unique. The standard model is not one of many possible theories that happen to fit the data. It is the essentially unique theory consistent with its symmetry group and the requirement of renormalizability. The particles fell out of constraints, not choices. That's what makes it extraordinary. And that's what makes its incompleteness so pointed. Because those constraints, which gave us everything we've ever detected, apparently say nothing about dark matter or gravity. The matter content of the standard model consists of quarks and leptons. Both are spin 1/2 fermions, particles that obey the Pauli exclusion principle, that build structure, that form the substance of things. They come in 2 types and 3 generations. The first generation, the up quark and down quark, which combine to form protons and neutrons, the electron and the electron neutrino. This is the matter that builds you, the chair you're sitting in, the planet under you, the stars in the sky. Everything visible in the universe is first generation matter. The second generation is identical in structure, same quantum numbers, same interactions, but heavier. The charm quark and strange quark, the muon and muon neutrino. The muon is identical to the electron in every way except mass. It's about 207 times heavier. It decays in microseconds. Why does it exist? The standard model doesn't say. It's just there. The third generation is heavier still, the top and bottom quarks, the tau and tau neutrino. The top quark, the heaviest known elementary particle, has a mass of about 173 giga-electron volts, heavier than an entire tungsten atom concentrated in a point-like object. It decays so quickly it doesn't even form hadrons before it vanishes. 3 generations, identical in structure, differing only in mass. The standard model predicts none of this. It accommodates 3 generations because that's what's observed, but provides no reason why 3 rather than 2 or 5. This is one of the most conspicuous, unexplained patterns in fundamental physics. Quarks carry a property called color charge, red, green, blue, in a metaphor that has nothing to do with actual color. Color charge is what couples to the strong force, and quarks are confined. The strong force between quarks grows with distance rather than weakening. Attempt to separate 2 quarks, and the energy required becomes sufficient to produce a new quark-antiquark pair. You never get a free quark, you get a new meson. Confinement is self-reinforcing. Leptons carry no color charge. The charged leptons, electron, muon, tau, interact electromagnetically. The neutrinos interact only via the weak force. They are the most weakly interacting particles in the standard model. Right now, trillions of solar neutrinos are passing through your body every second. The probability that any of them interacts with any of your atoms is vanishingly small. They go straight through you, through the Earth, largely through everything. Now, the forces. And here is where the standard model becomes genuinely beautiful. The forces are not added to the theory as separate ingredients. They emerge from the symmetry. Here's the principle. The standard model symmetry group, SU3 times SU2 times U1, can be imposed globally. The same transformation everywhere in space at the same time. Or it can be imposed locally, independently at every point in spacetime. Requiring local symmetry, gauge invariance, is a much stronger demand, and when you impose it, mathematics forces the existence of new fields. These fields, gauge fields, are required to compensate for the variation of the symmetry transformation from point to point. Their excitations are the force-carrying particles. One local symmetry demands one gauge field. Its excitation, the photon. Electromagnetism falls out of one gauge invariance, not as an assumption, as a mathematical necessity. SU2 local symmetry demands 3 gauge fields. Their excitations, the W+, W-, and Z bosons, the carriers of the weak force. 3 bosons because SU of 2 has 3 generators. SU of 3 local symmetry demands 8 gauge fields. Their excitations, the 8 gluons of the strong force. 8 because SU3 has 8 generators. The number of force carriers is not a choice. It's a consequence of the symmetry group's mathematical structure. You cannot have a different number of gluons while keeping SU3. The theory is rigid. At high energies, above the electroweak symmetry breaking scale, the photon, W, and Z bosons are manifestations of a single unified electroweak force. Below that scale, the Higgs field gives mass to the W and Z, separating them from the massless photon. What looks like 2 distinct forces at low energy, electromagnetism and the weak force, is one force at high energy. This unification was predicted mathematically in the 1960s. The W and Z bosons were found at CERN in 1983 at exactly the masses the theory predicted. The prediction came more than a decade before the discovery. The Higgs field sits at the center of the standard model's architecture and at the center of its deepest problem. Without the Higgs field taking a non-zero value in the vacuum, the electroweak symmetry would be unbroken. The W and Z bosons would be massless. The electromagnetic and weak forces would be indistinguishable at all energies. Elementary particles, quarks, leptons, would also be massless. Atoms could not form. Chemistry would be impossible. You would not exist. The Higgs field's non-zero vacuum value spontaneously breaks the electroweak symmetry. This is not imposed externally. The Higgs potential has its minimum away from zero, and the field naturally settles there. As it does, it differentiates the photon from the W and Z and couples to quarks and leptons to give them their masses. The strength of each particle's coupling to the Higgs field determines its mass. The top quark couples strongly, it's heavy. The electron couples weakly, it's light. The photon doesn't couple at all, it's massless. The Higgs boson, predicted in 1964, sought for nearly 50 years, found in 2012 at CERN's Large Hadron Collider, is the quantum excitation of this field. Its discovery was not a surprise. It was a confirmation of a mechanism the theory had required for decades. But its mass, 125 giga-electron volts, sits in a position of extraordinary fine-tuning. Quantum corrections from virtual particles should push the Higgs mass up to the Planck scale, about 10 to the power of 19 giga-electron volts. The cancellation that keeps it at 125 giga-electron volts requires 17 decimal places of precision with no mechanism to enforce it. This is the hierarchy problem. The standard model has no answer. Every proposed solution, supersymmetry, compositeness, extra dimensions, has so far failed to appear in experiment. The Higgs is simultaneously the standard model's greatest confirmed prediction and its most honest admission of what it doesn't understand. Let me be precise about what this theory has actually achieved, because greatest achievement needs to be earned with specifics. The anomalous magnetic moment of the electron, a tiny correction to how strongly the electron behaves as a magnet, arising from its interaction with the vacuum, is predicted by quantum electrodynamics to 11 significant figures. The experimental measurement matches to the same precision. There is no other agreement between theory and experiment in any field of science that approaches this level. The electroweak theory predicted the W boson mass and Z boson mass before those particles were found. The predictions were specific. The particles appeared at exactly the right masses. The existence of the charm quark was predicted in 1970, before it was detected, from the requirement of internal consistency, the GIM mechanism. It was found in 1974. The top quark's existence was inferred from the theory's structure decades before it was heavy enough to be produced, found in 1995. The Higgs, predicted 1964, found 2012. In each case, the standard model made specific, quantitative, ahead-of-time predictions about particles that did not yet exist experimentally, and in each case the particles appeared, exactly as predicted. This is not curve fitting. This is genuine prediction. This is what distinguishes physics from phenomenology. And now the silence. Gravity. The standard model contains no description of gravity. General relativity describes gravity as the curvature of space-time, a geometric theory with no quantum structure. Quantum field theory describes the other three forces as gauge theories with force-carrying bosons. Every attempt to combine them, to write a quantum field theory of gravity in the standard model framework, produces non-renormalizable infinities that cannot be absorbed. The two greatest theories of the 20th century are, at high energies, mathematically incompatible. Dark matter. The standard model has no particle that fits the observational profile of dark matter, present in halos around galaxies, gravitationally active, electromagnetically invisible. Whatever dark matter is, it's outside the standard model. Dark energy, the cosmological constant, the accelerating expansion of the universe. The standard model's vacuum energy calculation gives an answer 122 orders of magnitude too large. Nothing in the theory explains the small observed value. Matter-antimatter asymmetry. The standard model contains a small asymmetry between matter and antimatter, CP violation, but not nearly enough to explain why a universe that began symmetrically is now made almost entirely of matter. The 19 free parameters, the masses of 12 fermions, 4 mixing angles, 3 coupling constants, all measured, none derived. A deeper theory would explain them. The standard model uses them. What does this mean? It means the standard model is the map we drew of everything our instruments could reach, and it is an extraordinary map, precise, consistent, predictively powerful in its domain. But outside its domain, in the 95% of the universe's energy content it doesn't describe, in the quantum gravity regime it can't reach, in the generation structure it can't explain, the map is blank. We are not at the end of physics. We are at the edge of what the standard model can see, looking out into territory it was never built to describe. That boundary between what the standard model illuminates and what lies beyond it is not a failure. It is the most precisely defined frontier in science. We know, with extraordinary exactness, where our best theory stops working. That's not ignorance. That's the most honest kind of knowledge physics produces. The standard model is where our understanding is deepest and our instruments are sharpest. The darkness beyond it is where physics is most alive.